Okay, this is the next part to this lesson, and this is the longest one. It's the last one. And I wanted to make sure I solidified in your mind all the differences when we first started chapter 11, which was with the difference quotient. And this chart here is from your textbook, and I really liked it. It has a different quotient on the left and derivative on the right, and the terminology that applies to both. Now, I've used them intermittently, and I hope I haven't messed up anything in your categories of the importance of the difference. The difference quotient was first used for the slope of a secant line, the average rate of change, average velocity, average rate of change in cost, revenue, and profit. We did all of those primarily in section 11.3. And now that we're in 11.4, and we finished 11.3 with the definition of derivative and the many structers of derivative. In other words, we went through f prime of x, which is what we use on this one, dy dx, which I like because it's the tangent identification for slope, and then cap f prime x, and others that they had. Well, to get the derivative, we added the limit as h approaches 0 to the difference quotient. And the terminology used specifically for derivative is slope of a tangent line, instantaneous rate of change, velocity, marginal cost, revenue, or profit. So we can see the distinctions in the growth of application. We also found out that to get f prime of x from a definition of derivative, we first have to put the function plus x every h for every x in the function, then subtract the original function from that output, and then divide by the h, and then take the limit. And remember, we have to make sure we factor out the h, otherwise the derivative does not exist. Now we're at this point. This is the new material, and here we go. The existence of a derivative. In a derivative, there has to be continuity within the function. Before, we could take a limit and there could be a hole, but here we're talking continuity. F is continuous. In other words, there's no break. So I can have a curve like this, and it's continuous from this point to this point, and anywhere in this we can find a derivative. It is smooth, and f does not have a vertical tangent line. In other words, a vertical means x equals a number. So what that means is that we can have this occur. This would have this happen. All right. The definition does not exist when any of the following have. It is discontinuous, right there, discontinuous. It has a sharp corner, and we call that a cusp in Cal 2. And the function has a vertical tangent line, vertical, up and down, that guy. Here. And here is a picture that described it, and I really like this picture. If you notice, it is discontinuous here. There are no tangents because these are peaks. It is from here to here, but it is discontinuous there because they're going into infinity. So therefore, the function cannot be defined. The function is not defined on any open hole, like I said. And a vertical tangent means that we have a vertical line at x equals some constant. So they cannot take a derivative of that. So here we have an example that we want to do. Find the value or values of x where the graph does not have a derivative. Well, the curvatures are fine, but this is at the cusp. So at x equals 0, it is undefined, no derivative. possible. All right. So in this one, we're looking at rational function, and we know we can't have a number divided by 0 because it is undefined. So therefore, we have some kind of break in the graph at, we set the denominator equal to 0 and solve. So then we have x minus 7 cannot equal 0, so x cannot equal 7. So where x equals 7, the function has no derivative. We would factor and say the limit could exist if it was approaching the same value. But in this case, these are vertical. It's a vertical asymptote, and also it is the top is not factorable. So, using the definition of derivative, find f prime of x, then find f prime of 5, 0, and 3. Okay, now we know that x cannot equal 0. It's where it is undefined. But everywhere else, it is defined. So what we're going to do is take the derivative. And this example introduces some mathematical processes that are valuable for doing derivatives. So we want f prime of x, and that's going to be 100 over x plus h minus 100 over x, all divided by h. Now what we need here is to multiply out the denominators by an LCM, the least common multiple. And of course it's going to be x times x plus h, because that's the common denominator. And so we're going to multiply the top and bottom by the LCM. Now, if I multiply this to that, I'm going to be left with 100x. And if I multiply this times that, I'm going to end up with 100 minus, I'm sorry, sorry, 1 minus time, 100 times the x plus h. And this is divided by h, x times x plus h. All right. So now, remember this is f prime of x, and I forgot to put in as the limit of h approaches 0, and I'm sorry about that. So let's continue on and do some math. So this is going to be 100x minus 100x minus 100h, all over h times x plus h. All right. Well, we notice that these are additive inverses. So now I'm left with the f prime of x equals the limit as h approaches 0 of a negative 100h over h times x plus h. So I cancel out the h's, and I'm left with, now later on we're going to do the rules in the second portion of this course, and we'll do all the quick and dirty rules so we can cut to the quick. 100 negative 100 over x times x plus h. Now I'm going to insert 0 for h, And that's going to give me a negative 100 over x times x plus 0, which leaves it as x. And I'm going to do it right here. I get a negative 100 over x squared. And this is the derivative. So now that I know the derivative, I am going to find f prime of negative 5. So that's going to be a negative 100 over 25, which gives me a negative 4, if I did the math right. So I'm going to have a negative 4 for that. And now I'm going to do the next one, f prime of 0. Well, that is undefined, so it does not exist. There is no derivative possible for that. Then I'm going to do f prime of 3. So for that, it does exist and it does work. All right. So I'm going to stop right there. I went further than my I will continue on for the next one. Thank you for listening.